I'm going to be telling you about clutters, which are also known as anti-chains and spurner families, and this is joint work with Dylan Mayhew. So first off, what is a clutter? What you have is a finite set E, and then you've got a collection of subsets of this set, so that if you take any two of the subsets, then neither one is contained inside the other one. And for examples, you could take your collection of subsets to be the set of circuits of a matroid, or you could take it to be the set of bases of a matroid. And so since matroids are coming up, you could be asking, do clutters have minors, just like graphs and matroids do? And the answer is, of course, yes. We've got deletion and contraction, just like always. And so with deletion, to get your new collection of subsets, you take all of the old ones which don't contain the element you're deleting. Well, with contraction, you first take all of your original subsets, remove your element from them, and then you just keep the ones which are minimal under subset inclusion. And if you've got a whole bunch that you're deleting and contracting, then the order in which you do these doesn't matter, just like with matroids. In my title, I mentioned connected clutters, and these are just a generalization of connected matroids. So my clutter is going to be connected if and only if it has no separation. And by a separation, I mean a partition of the set E into two parts, so that every one of my subsets is either in the first part or it's in the second part. And now, even though this is a generalization of matroid connectivity, not all properties which matroids have are going to extend to clutters. So for instance, we've got this really useful theorem here, which says that if you've got some connected matroid and you take any element inside that, then either the deletion or the contraction is going to be connected as well. And this is something which doesn't hold for clutters. And here is a counterexample for that. So this is for a clutter where all of the subsets have cardinality 2, and that means I can represent the clutter as a graph, like I've drawn here. So my vertices of the graph correspond to the elements of the set E, and the edges of the graph correspond to the subsets of the clutter. And then the incidence relation is exactly what you'd guess it would be. I have an edge going to a vertex if and only if the element represented by the vertex is inside the subset represented by the edge. So it's just the incidence graph. And it's an easy exercise to check that the clutter is going to be connected if and only if this graph is connected. And so this clutter here is connected, and I've picked out that element V at the top there, and that's one vertex where if I delete it or I contract it, in both cases I get a disconnected graph and therefore a disconnected clutter. So here is the deletion in black. So what we do there is we remove the element, so we delete that vertex V, and then we only keep the subsets which don't contain that element. And so any edge which was incident with V gets removed from the graph. The contraction graph is a bit more complicated looking, so we still remove the vertex V, and now we take all of the original subsets, remove the element V from them, and so we had two element subsets to start with, so that's going to create a bunch of one element subsets, and that's where these loops come from. So basically every edge which was originally incident with V turns into a loop attached to the other vertex at the end of that edge. And then that's not quite the whole thing, because then we just take the subsets once we've done that which are minimal under subset inclusion. And so for instance, this edge which was originally down here disappears because that represents the two element subset with that element and that one. And we've also got that loop with the one element subset. So we get rid of the bigger subset and so delete that edge. I'm not going to talk about any more definitions with clutters, and I'll instead go on to talking about splitter theorems. So yesterday, James told us about Seymour's splitter theorem for 3 connected matroids. And you get a whole bunch of other splitter theorems as well, which are all named after that original one. And the one I'm concerned with is this one up here, which was proved independently by Brailovsky and Seymour. And so that says you've got some connected matroid, and then you've got another connected matroid contained inside that one. And the theorem says that there's some element in your big matroid M, so that either the deletion or the contraction is also connected. And furthermore, you still have this second smaller matroid as a minor still. And what's surprising, given the previous false result I mentioned, is that this one actually does generalize to clutters. So this is the exact same result, but up here I've got the word clutters when previously there was the word matroids. And I don't have time to go through the proof of that, of course, but I'll just say that it's done by looking at the incidence graph again, like in the previous counterexample, and looking at the structure of that. But of course, in general, not all subsets in your clutter are going to have cardinality too. And so what we do instead is create a bipartite incidence graph, where we've got one vertex class representing the elements, and one vertex class representing the subsets. And then the edge relation is, again, exactly what you'd think it would be.
Are there any?
Yeah, I just wanted, so you say it has an n as a minor. Do you really mean that, or do you mean it has a minor isomorphic?
As a minor.
You're not going to change the elements that you're contracting?
No, so as a minor.
What about free connectors? Define free connectors for clutter?
You possibly can. It hasn't been done yet. I was just talking to Dylan about it, actually. And so the problem with our notion of connectivity is that it doesn't respect duality with the blocker of the clutter. And so for 3 connected, you'd have to take care of that as well. So I'm sure it can be done, and it could be something to do in the future.